Hello from sleepy Seattle. Welcome to another Sleep Facts video. We hope you enjoy these sleepy facts about the universe and drift into a wonderful sleep. Part 1. The beginning of everything. Before there were stars, before there were planets, before there was even light, there was nothing. Not empty space, because space did not yet exist, and not darkness, because darkness needs light to be absent. There was simply no time, no distance, no direction. And then, around 13.8 billion years ago, everything began at once. This moment is known as the Big Bang, not an explosion in space, but the birth of space itself. The universe did not expand into anything. It created its own space as it expanded, stretching outward in every direction at the same time. Even now, the universe is still expanding, and not slowing down, but accelerating as distant galaxies drift farther apart with every passing moment. In the very first fraction of a second after the Big Bang, the universe was unimaginably hot, hotter than the core of any star, and everything that would ever exist was compressed into a space smaller than an atom. As the universe cooled, the first subatomic particles formed, followed by the simplest atoms, mostly hydrogen and helium, the two elements that still make up most of the universe today. These atoms drifted through the vast darkness for hundreds of millions of years. There were no stars yet, no planets, no galaxies, just quiet clouds of gas, slowly gathering under the gentle pull of gravity, the force that would become the great sculptor of the cosmos. Where gas became slightly denser, gravity pulled in more matter, until the first stars ignited. When those first stars switched on, the universe lit up for the very first time. These earliest stars were enormous, many times larger than our sun, and they burned fast and bright. Inside their cores, simple elements fused into heavier ones: carbon, oxygen, nitrogen, the building blocks of planets, of oceans, and eventually, of life. When these stars reached the end of their lives, they exploded in powerful supernovae, scattering those elements across space. Every atom of carbon in your body, every atom of oxygen you breathe, was once forged inside a star. You are, quite literally, made of stardust. Over time, gravity gathered stars together into vast cities of light called galaxies. Some galaxies are spiral-shaped, with graceful arms winding outward. Others are elliptical, smooth, and ancient. Some are chaotic, colliding and reshaping each other over billions of years. Our home galaxy is the Milky Way, a barred spiral galaxy containing over 100 billion stars, and likely even more planets. The Milky Way is so large that light takes 100,000 years to travel from one side to the other. And yet, it is only one galaxy among an estimated 2 trillion galaxies in the observable universe. Each of those galaxies contains billions of stars, and many of those stars host planetary systems of their own. This means that planets are not rare, they are likely the rule, not the exception. Astronomers now believe there may be more planets in the universe than stars. Some orbit calmly in stable systems. Others wander alone, rogue planets drifting through space without a star at all. Within the Milky Way, about 2/3 of stars are thought to have planets, and many of those planets lie within what scientists call the habitable zone, where temperatures might allow liquid water to exist. Water, the quiet ingredient that makes life as we know it possible. Our sun formed about 4.6 billion years ago, from a cloud of gas and dust enriched by earlier generations of stars. As the sun ignited, the leftover material flattened into a spinning disk, and within that disk, planets slowly took shape. Rock clumped with rock. Ice gathered with ice. Gravity pulled everything inward, patiently. From this slow dance of dust and time, our solar system was born. 8 planets settled into stable orbits, each one unique, each one telling a different story of temperature, gravity, and time. At just the right distance from the sun, on a small rocky world called Earth, water pooled on the surface. The planet cooled. Oceans formed. And chemistry began to experiment. Life did not appear suddenly. It unfolded gradually, over billions of years, guided by chance, physics, and persistence. And here we are, thinking beings on a tiny planet, orbiting an ordinary star, inside one galaxy among trillions. When you look up at the night sky, you are not just seeing distant lights. You are seeing time itself. Because the light from those stars has traveled for years, for centuries, sometimes for millions of years, before reaching your eyes. To observe the universe is to look into the past. And this is only the beginning of our journey. In the next chapter, we will travel deeper into our solar system, to the planets, their moons, their storms, and their secrets. For now, rest with the knowledge that you exist in a universe vast beyond imagination, and yet intimately connected to you in every atom of your being. Part 2. Our Star and the Inner Worlds. At the center of our solar system is a star so familiar that we often forget what it truly is. The Sun. It is not a flame, and it does not burn in the way fire does. Instead, deep within its core, hydrogen atoms are pressed together by immense gravity, fusing into helium and releasing enormous amounts of energy. Every second, the Sun converts about 4 million tons of matter into pure energy, radiating light and heat outward in all directions. That energy takes around 8 minutes to travel the distance from the Sun to Earth, crossing nearly 150 million kilometers of space. The sunlight touching your skin right now began its journey before you even noticed the day unfolding. The Sun accounts for more than 99.8% of the total mass of the entire solar system. Everything else, the planets, moons, asteroids, and comets, orbit in response to its gravity, held gently but firmly in place. And yet, the Sun itself is only an average star. There are stars far larger, far hotter, and far brighter scattered throughout the galaxy. Still, for Earth, the Sun is everything. Its energy drives the winds, the ocean currents, the growth of plants, and the delicate balance of life itself. Closest to the Sun is Mercury, a world of extremes. Mercury has no thick atmosphere to trap heat, so its surface temperatures swing dramatically, from scorching days to freezing nights. A single day on Mercury lasts longer than its entire year, as the planet rotates slowly while racing around the Sun. Mercury's surface is scarred with craters, remnants of ancient impacts from the early solar system, preserved almost unchanged for billions of years. Next comes Venus, a planet often called Earth's twin, similar in size, yet radically different in nature. Venus is wrapped in thick clouds of sulfuric acid, and beneath them, a runaway greenhouse effect has turned the planet into the hottest surface in the solar system. Even though Mercury is closer to the Sun, Venus is hotter. Its surface temperatures are hot enough to melt lead. Venus rotates so slowly that its day is longer than its year, and it spins in the opposite direction to most other planets. The Sun would rise in the west and set in the east. Long ago, Venus may have had oceans. But over time, solar radiation stripped away its water, leaving behind a dry, crushing atmosphere more than 90 times thicker than Earth's. Then comes Earth. From space, it appears as a pale blue sphere, wrapped in clouds, with oceans covering more than 70% of its surface. Earth sits in a delicate region known as the Goldilocks zone, not too hot, not too cold, but just right for liquid water to exist. Its atmosphere protects life by filtering harmful radiation and regulating temperature. Its magnetic field, generated deep within its core, shields the planet from charged particles streaming outward from the Sun. Without this invisible protection, Earth's atmosphere could slowly be stripped away, as happened on Mars. Earth is also unique in having active plate tectonics, moving continents that recycle carbon, reshape the surface, and help stabilize the climate over geological time. Life here has survived mass extinctions, ice ages, and asteroid impacts, persisting through change rather than resisting it. Orbiting Earth is the Moon, our constant companion. The Moon stabilizes Earth's axial tilt, keeping seasons relatively predictable. Its gravitational pull drives the ocean tides, moving vast amounts of water twice each day. The Moon is slowly drifting away from Earth at about 3.8 centimeters per year, a gentle widening of the distance between them. When you see the Moon, you are seeing a world that always shows us the same face, locked in a gravitational embrace that has lasted for billions of years. Beyond Earth lies Mars, the red planet. Mars once had rivers, lakes, and possibly even oceans. Today, it is cold and dry, with a thin atmosphere and vast deserts of iron-rich dust. Mars hosts the tallest volcano in the solar system, Olympus Mons, nearly 3 times the height of Mount Everest. It also bears a canyon system so vast that it would stretch across entire continents on Earth. Scientists continue to search Mars for signs that life may have once existed there, or perhaps still survives beneath the surface. Together, these inner planets tell a story of divergence, how worlds formed from the same material can evolve in dramatically different ways depending on atmosphere, distance, and time. They remind us that habitability is fragile, and that Earth's balance is both rare and precious. In the next chapter, we will move beyond the rocky worlds and journey outward to the giant planets, to swirling storms, ring systems, and moons that may hide oceans beneath ice. For now, take a moment to rest in the quiet realization that everything we know, everything we are, exists within this small region of space circling an ordinary star in a vast and ancient galaxy. Part 3. The Giant Worlds and Their Moons. Beyond the orbit of Mars, the nature of the solar system changes. The small, rocky worlds give way to giants, planets so massive that they reshape space around them through sheer gravitational presence. The first of these giants is Jupiter. Jupiter is the largest planet in the solar system, more massive than all the other planets combined. Its immense gravity acts as both guardian and threat, deflecting many asteroids and comets that might otherwise reach the inner planets, while also pulling countless objects into its domain. Jupiter is not solid. It is a vast sphere of gas and liquid, mostly hydrogen and helium, with pressures so intense that hydrogen behaves like a metal deep within. One day on Jupiter lasts less than 10 hours, making it the fastest spinning planet in the solar system. This rapid rotation drives powerful winds that wrap the planet in colorful bands and colossal storms. The most famous of these storms is the Great Red Spot, a vast cyclone that has been raging for at least 3 centuries, large enough to swallow Earth whole. Jupiter is also a world of moons. It has over 90 known moons, each one a unique environment. Among them is Europa, a small icy moon with a smooth, fractured surface. Beneath Europa's ice lies a global ocean of liquid water, kept warm by tidal heating caused by Jupiter's immense gravity. This hidden ocean may contain more water than all of Earth's oceans combined, making Europa one of the most promising places to search for life beyond Earth. Another of Jupiter's moons, Io, is the most volcanically active world in the solar system. Its surface is constantly reshaped by eruptions driven by gravitational stretching, with lava lakes and towering plumes rising hundreds of kilometers into space. Next is Saturn, the planet of rings. Saturn is less dense than water. If there were a bathtub large enough, it would float. Its iconic rings are made of countless pieces of ice and rock, ranging in size from tiny grains to mountains. Though they appear solid, the rings are thin, in many places only tens of meters thick, yet they stretch hundreds of thousands of kilometers wide. Saturn, like Jupiter, is surrounded by a vast family of moons. One of the most intriguing is Titan. Titan has a thick atmosphere richer in organic molecules than any moon in the solar system. On its surface, liquid methane and ethane flow through rivers, fill lakes, and fall as rain, forming a chemical cycle similar to Earth's water cycle, but at much colder temperatures. Another moon, Enceladus, is small and bright, with a surface of fresh ice. Jets of water vapor erupt from cracks near its south pole, spewing material into space. These plumes originate from a subsurface ocean, making Enceladus another prime candidate in the search for extraterrestrial life. Beyond Saturn lies Uranus, a planet that appears calm and pale blue, but hides a strange secret. Uranus is tilted on its side by about 98 degrees, likely due to an ancient collision. As a result, its poles take turns facing the Sun for decades at a time, leading to extreme seasonal changes that last for years. Uranus is an ice giant, containing large amounts of water, ammonia, and methane under high pressure. Farther still is Neptune, the most distant known planet in our solar system. Despite receiving little sunlight, Neptune has the fastest winds ever recorded on any planet, exceeding 2,000 kilometers per hour. Its deep blue color comes from methane in its atmosphere, absorbing red light and reflecting blue. Neptune radiates more energy than it receives from the Sun, suggesting an internal heat source still active deep within. Together, these giant planets and their moons expand our understanding of what worlds can be. They show us oceans without sunlight, weather systems lasting centuries, and chemistry far stranger than anything on Earth. They remind us that life, if it exists elsewhere, may not follow familiar rules. In the next chapter, we will move beyond the planets entirely, to asteroids, comets, and the distant edge of the Sun's influence, where our solar system fades into interstellar space. For now, let the vastness of these worlds settle quietly in your mind, giants moving in slow harmony, circling a star that has watched them for billions of years. Part 4. The Small Bodies and the Edge of Home. Beyond the giant planets, the solar system begins to thin. The warmth of the Sun fades, and what remains are smaller, quieter worlds, fragments left behind from the time of planetary formation. Between Mars and Jupiter lies the asteroid belt. Here, millions of rocky bodies orbit the Sun, ranging in size from dust grains to objects hundreds of kilometers wide. Contrary to popular imagination, the asteroid belt is not crowded. The distances between asteroids are vast, and spacecraft can pass through safely without weaving or dodging. These asteroids are remnants, material that never became a planet, their growth disrupted by Jupiter's immense gravity. Some asteroids are rich in metals, others in carbon and water-bearing minerals, offering clues to the early chemistry of the solar system. Occasionally, gravitational nudges send asteroids inward, crossing Earth's orbit. Most burn up harmlessly in the atmosphere, creating brief streaks of light, meteors, often called shooting stars. Very rarely, larger objects reach the surface, leaving impact craters and reminders that Earth exists within a dynamic cosmic environment. Farther out still, beyond Neptune, lies the Kuiper Belt. This vast, disc-shaped region is populated by icy bodies left over from planetary formation. Among them is Pluto, once considered the ninth planet, now classified as a dwarf planet. Pluto follows an elongated, tilted orbit, sometimes coming closer to the Sun than Neptune, and sometimes drifting far into the cold darkness. Despite its small size, Pluto is surprisingly complex, with mountains of ice, vast plains of frozen nitrogen, and evidence of a possible subsurface ocean. Pluto is not alone. The Kuiper Belt contains many dwarf planets, each one a frozen world preserving conditions from the early solar system. Beyond even the Kuiper Belt lies the Oort cloud, a distant, spherical halo surrounding the solar system. The Oort cloud is thought to extend up to a light-year away from the Sun, marking the farthest boundary of its gravitational influence. This is the source of long-period comets, icy visitors that take thousands or even millions of years to complete a single orbit. When a comet is nudged inward, the Sun's warmth awakens it. Ice begins to vaporize, releasing gas and dust, forming a glowing coma and a long, luminous tail. A comet's tail always points away from the Sun, shaped by solar radiation and the solar wind. These fragile travelers carry some of the most pristine material from the birth of the solar system. Many scientists believe that comets may have played a role in delivering water and organic molecules to early Earth. In this way, the ingredients for life may have arrived from the coldest, darkest regions of space. The Sun's influence does not end abruptly. It extends outward in a vast bubble called the heliosphere. This region is shaped by the solar wind, a constant stream of charged particles flowing outward from the Sun. At the edge of this bubble, the solar wind slows and meets the interstellar medium. This boundary is known as the heliopause. In 2012 and 2018, the Voyager 1 and Voyager 2 spacecraft crossed this threshold, becoming the first human-made objects to enter interstellar space. They continue to travel outward, carrying golden records, messages from Earth intended for any future intelligence that might one day find them. Beyond the heliopause, the Sun becomes just another star among billions. Its light fades into the background glow of the Milky Way. Here, our solar system blends into the broader galaxy, no longer distinct, no longer sheltered. And yet, even at this distant edge, gravity still whispers, holding the last remnants of our cosmic neighborhood. In the next chapter, we will leave the solar system entirely and journey outward into the structure of the Milky Way itself, to star-forming regions, stellar deaths, and the slow rotation of our galactic home. For now, rest with the understanding that even the smallest fragments of space, dust, ice, wandering rocks, carry the memory of how everything began. Part 5. The Milky Way, our galactic home. Having reached the edge of the solar system, we now step fully into the wider galaxy. The Milky Way is a barred spiral galaxy, its luminous arms sweeping outward from a dense central core. From Earth, we see it as a pale river of light stretching across the night sky, the combined glow of countless distant stars too faint to distinguish individually. The Milky Way contains more than 100 billion stars, along with vast clouds of gas and dust from which new stars continue to form. It rotates slowly, completing a single rotation roughly every 225 to 250 million years. The last time the Milky Way was in the same orientation it is today, dinosaurs were just beginning to walk the Earth. Our solar system lies about 27,000 light-years from the galactic center, embedded in a minor spiral arm known as the Orion Arm. As we orbit the center of the galaxy, we travel at about 230 kilometers per second, carried along in a grand, invisible current of stars. At the heart of the Milky Way lies Sagittarius A*, a supermassive black hole with a mass roughly 4 million times that of our Sun. Despite its immense mass, this black hole does not actively consume everything around it. It remains relatively quiet, its presence revealed by the motion of nearby stars tracing tight, graceful orbits around it. Black holes are not cosmic vacuum cleaners. They only exert strong gravitational pull very close to their boundaries. From a safe distance, they behave much like any other massive object. Throughout the Milky Way, stars are born in vast, cold clouds called nebulae. Within these clouds, gravity slowly draws material together until pressure and heat ignite nuclear fusion. When a star is born, it begins a life cycle that can last millions or billions of years, depending on its mass. Smaller stars, like the Sun, burn steadily and calmly, while massive stars live fast, shine brilliantly, and die young. When massive stars exhaust their fuel, they collapse and explode in spectacular supernovae. These explosions create and scatter heavy elements throughout the galaxy, the raw materials for future stars, planets, and life. Some supernova remnants form neutron stars, objects so dense that a single teaspoon of their material would weigh billions of tons on Earth. Others collapse further, forming stellar mass black holes. Throughout the Milky Way, stars are rarely isolated. Many exist in binary or multiple star systems, orbiting one another in delicate gravitational dances. Planets, too, are common. Astronomers have discovered thousands of exoplanets orbiting stars beyond our solar system, with sizes and compositions ranging from rocky worlds to gas giants orbiting perilously close to their stars. Some exoplanets exist in extreme conditions, with molten surfaces, perpetual darkness, or temperatures colder than deep space. Others may be more Earth-like, raising profound questions about the possibility of life elsewhere in the galaxy. The Milky Way is not static. It grows and evolves by absorbing smaller galaxies through gravitational mergers. Streams of stars found throughout the galaxy are remnants of ancient collisions, fossil records of past encounters. In the distant future, the Milky Way will collide with the Andromeda Galaxy, our nearest large galactic neighbor. This collision, expected in about 4.5 billion years, will reshape both galaxies, though individual stars are unlikely to collide. The night sky will slowly transform as new constellations emerge from the cosmic rearrangement. For now, the Milky Way remains our home, a vast, rotating city of stars filled with birth, death, and quiet persistence. In the next chapter, we will leave our galaxy behind and journey outward to the wider universe, to clusters of galaxies, cosmic filaments, and the large-scale structure that connects everything. For the moment, rest with the awareness that your life unfolds within this immense galactic system, a small part of a much larger story, written in light and gravity. Part 6. The Cosmic Web and the Shape of Everything. As vast as our galaxy is, it is only a single point in a much larger pattern. When astronomers began mapping the universe on its grandest scales, they discovered something unexpected. Galaxies are not scattered randomly. They gather into groups, clusters, and enormous chains stretching across billions of light-years. These vast structures form what is known as the cosmic web. Long filaments of galaxies thread through space, meeting at dense intersections where galaxy clusters reside. Between these filaments lie enormous voids, regions of space nearly empty of galaxies, spanning tens of millions of light-years. The cosmic web traces the influence of an invisible substance called dark matter. Dark matter does not emit light, absorb light, or reflect it. We cannot see it directly, and yet, its gravitational pull shapes the universe. Galaxies rotate too fast to be held together by visible matter alone. Without dark matter, they would fly apart. Measurements suggest that dark matter makes up about 85% of all matter in the universe. It forms vast halos around galaxies, guiding where stars and gas can gather. Even larger than dark matter's influence is something even more mysterious. Dark energy. Dark energy is the name given to the force driving the accelerating expansion of the universe. It acts in opposition to gravity, stretching space itself, pushing distant galaxies apart. Dark energy accounts for roughly 70% of the total energy content of the universe. Everything we can see, stars, planets, gas, dust, makes up less than 5% of what exists. Most of the universe is composed of things we do not yet fully understand. When we observe distant galaxies, we are looking deep into the past. Because light takes time to travel, the farther away an object is, the older the light we see. Some of the galaxies observed today appear as they were over 13 billion years ago, shortly after the universe began. In this way, telescopes function as time machines, allowing us to witness cosmic history. The most distant light ever detected comes from the cosmic microwave background. This faint glow fills the universe in every direction. It is the cooled remnant of the early universe, released when space first became transparent, about 380,000 years after the Big Bang. The cosmic microwave background is remarkably uniform, yet it contains tiny fluctuations, minute differences in temperature that later grew into galaxies and clusters. These subtle patterns are the universe's earliest fingerprints. Over billions of years, gravity amplified them, drawing matter together into the cosmic web we see today. As the universe expands, the distances between galaxy clusters grow. Eventually, distant galaxies will move so far away that their light will never reach us. Future observers, billions of years from now, may see a universe largely empty and isolated. Cosmic expansion does not mean galaxies are flying through space. It means space itself is stretching, carrying galaxies along with it. On the largest scales, the universe appears flat, meaning its geometry follows the rules of Euclidean space. Whether the universe is infinite or simply extremely large remains unknown. Beyond the observable horizon, there may be regions of space forever inaccessible to us. And yet, everything we have ever known, every story ever told, every life ever lived, exists within this expanding cosmic structure. In the next chapter, we will turn inward again, toward time, toward the strange nature of relativity and the limits of what can be known about the universe itself. For now, let the scale of it all settle gently, a universe woven not from chaos, but from structure, balance, and mystery. Part 7. Time, Space-Time, and the Flow of Reality. Up to now, we have traveled through space. But the universe is not built from space alone. It is woven together with something just as fundamental, time. Space and time are not separate entities. They form a single structure called space-time. This insight comes from Albert Einstein's theory of relativity, which revealed that gravity is not a force pulling objects together, but a curvature in space-time itself. Mass bends space-time. The more massive an object is, the deeper the curve it creates. Planets orbit stars not because they are pulled, but because they follow curved paths through distorted space-time. Even time itself is affected by gravity. Clocks tick more slowly near massive objects than they do far away. This phenomenon, known as gravitational time dilation, has been measured experimentally. Clocks aboard satellites run slightly faster than identical clocks on Earth's surface. Without correcting for this effect, GPS navigation would drift by kilometers each day. Time is also affected by motion. According to special relativity, the faster an object moves through space, the slower it moves through time. At everyday speeds, this effect is imperceptible. But at speeds close to the speed of light, time dilation becomes dramatic. For an object traveling at near-light speed, time slows almost to a standstill relative to a stationary observer. Light itself experiences no passage of time. From a photon's perspective, its entire journey across the universe occurs instantaneously. The speed of light, about 300,000 kilometers per second, is not just a speed limit, it is a fundamental property of spacetime. Nothing with mass can reach or exceed it. This limit shapes how cause and effect propagate through the universe. It defines what can influence what, and when. Time, as we experience it, flows in one direction. This is known as the arrow of time. On the smallest scales, the laws of physics are mostly time-symmetric. They do not distinguish between past and future. Yet on large scales, time unmistakably moves forward. This direction is linked to entropy, a measure of disorder. The universe began in a highly ordered state. As time passes, entropy increases. Stars burn their fuel. Heat spreads. Structures slowly break down. This gradual increase in entropy gives time its forward direction. Black holes introduce some of the deepest questions about time and reality. According to relativity, time slows dramatically near a black hole's event horizon. To a distant observer, an object falling in appears to freeze in time. To the falling object, time continues normally, at least initially. What happens beyond the event horizon remains unknown. At the center of a black hole, our current theories break down. Here, space-time itself may end. Quantum physics adds another layer of mystery. At very small scales, time may not be smooth and continuous, but grainy and probabilistic. Some theories suggest that time itself emerges from deeper quantum processes. Whether time is fundamental or an emergent property is still an open question. The universe does not have a single, universal clock. Each observer carries their own version of time, shaped by motion and gravity. And yet, despite its flexibility, time binds us all. It marks beginnings and endings, growth and decay, memory and anticipation. In the next chapter, we will explore the strange quantum foundations beneath space-time, where certainty dissolves and reality behaves in ways that challenge intuition. For now, Rest with the quiet understanding that time is not something you move through. It is something you are part of. Part 8. The Quantum World and the Limits of Knowing. Beneath the vast structures of galaxies and spacetime lies a world far smaller and far stranger. This is the quantum realm. At these scales, the familiar rules of everyday experience begin to dissolve. Particles no longer behave like tiny solid objects. Instead, they act as probabilities, described not by certainty, but by likelihood. An electron, for example, does not orbit an atom's nucleus like a planet around a star. It exists as a cloud of probability, appearing only when measured. This is known as wave-particle duality, the idea that matter can behave as both a wave and a particle, depending on how it is observed. Light exhibits this dual nature as well, sometimes acting like a wave, sometimes like a stream of particles called photons. At the quantum level, observation itself matters. Measuring a system changes its outcome. This phenomenon is not due to faulty instruments, but is built into the structure of reality itself. According to the uncertainty principle, there are limits to what can be known simultaneously. The more precisely we measure a particle's position, the less precisely we can know its momentum, and vice versa. This is not a limitation of technology, but a fundamental feature of nature. Quantum particles can also become entangled. When two particles interact, their properties may become linked, no matter how far apart they later travel. Measuring one instantly affects the other, even across vast distances. Einstein called this spooky action at a distance. And yet, entanglement has been repeatedly confirmed by experiment. Despite this connection, entanglement does not allow information to travel faster than light. Causality remains intact, even if intuition struggles. Quantum fluctuations ripple through empty space. Even a perfect vacuum is not truly empty. Particles briefly appear and disappear, borrowing energy from the universe before vanishing again. These tiny fluctuations may have played a crucial role in shaping the early universe, seeding the structures that later became galaxies. At the smallest scales, forces merge. Electromagnetism and the weak nuclear force unify at high energies. Scientists continue searching for a deeper theory that unites all forces, including gravity, into a single framework. This goal is sometimes called a theory of everything. One challenge is that general relativity and quantum mechanics do not yet fully agree. Each works beautifully in its own domain, but their mathematical languages clash under extreme conditions, such as inside black holes or at the beginning of time. Some theories propose extra dimensions of space, curled up and hidden from view. Others suggest that space-time itself may be built from discrete units, like pixels of reality. Whether these ideas are correct remains unknown. Science advances not by certainty, but by refining questions. Every answer reveals new mysteries. Despite its strangeness, the quantum world underpins everything we experience. The solidity of matter, the stability of atoms, the chemistry of life, all emerge from quantum laws. Even your thoughts, your memories, your sense of self depend on these invisible processes playing out trillions of times each second. In the next chapter, we will return to a larger perspective, to life in the universe, the search for meaning, and the quiet question of whether we are alone. For now, rest with the knowledge that reality is deeper, subtler, and more interconnected than it first appears. Part 9. Life in a Vast Cosmos. After exploring the deepest laws of reality, a quiet question naturally arises. Is life unique to Earth, or is it woven throughout the universe? Life, as we understand it, requires a delicate balance, energy, chemistry, and time. On Earth, life appeared surprisingly early. Evidence suggests that simple life existed less than 500 million years after the planet formed. This implies that, under the right conditions, life may not be rare. Across the galaxy, astronomers have discovered thousands of exoplanets, planets orbiting stars beyond our Sun. Many of these worlds lie within their star's habitable zone, where liquid water could exist. Some exoplanets are rocky like Earth. Others are ocean worlds, covered entirely by deep global seas. Some orbit red dwarf stars, the most common type of star in the Milky Way, which can shine steadily for trillions of years. Life may also exist in places once thought impossible. Beneath the icy shells of moons like Europa and Enceladus, liquid oceans persist in darkness, heated by gravitational energy rather than sunlight. On Earth, life thrives in extreme environments: deep sea vents, acidic lakes, frozen tundra. These extremophiles expand our understanding of what life can tolerate. The chemistry of life is not limited to carbon alone, but carbon's versatility makes it particularly suited to forming complex molecules. Organic compounds have been found in meteorites, comets, and interstellar clouds. The building blocks of life appear to be widespread. And yet, despite these promising signs, the universe remains quiet. We have detected no confirmed signals from extraterrestrial civilizations. This puzzle is known as the Fermi paradox. If intelligent life is common, why does the universe appear so silent? Many possibilities exist. Civilizations may be rare. They may destroy themselves. They may communicate in ways we do not yet understand. Or they may simply be too far apart in space and time to ever intersect. Radio signals fade. Civilizations may be brief. The cosmos is vast. Search efforts continue. Scientists listen for narrowband signals, scan for atmospheric signatures, and study distant worlds for chemical imbalances that might indicate life. For now, Earth remains the only known world to host conscious observers. This does not make us central, but it does make us precious. In the next chapter, we will look forward to the long future of the universe and the fate that awaits stars, galaxies, and time itself. Part 10. The far future of everything. The universe is not only vast in space. It is vast in time. Stars are born, shine, and eventually fade. Our Sun, currently middle-aged, will continue burning for about 5 billion more years. When its fuel begins to run low, it will expand into a red giant, engulfing or scorching the inner planets. Eventually, it will shed its outer layers, leaving behind a glowing planetary nebula and a dense white dwarf at its center. Across the universe, star formation will gradually slow. Gas will be used up or locked away in long-lived stellar remnants. The brightest era of the cosmos is happening now. In the far future, new stars will become rare. Galaxies will drift farther apart as cosmic expansion accelerates. Eventually, distant galaxies will slip beyond the observable horizon, their light stretched into darkness. Black holes will dominate the distant future. They will slowly evaporate through a process known as Hawking radiation, taking unimaginably long timescales to disappear. A supermassive black hole may take longer to fade than the current age of the universe by many orders of magnitude. Some theories predict a future known as the heat death of the universe, a state of maximum entropy, where energy is evenly spread and no useful work can be done. Others propose alternative endings, a big crunch, a big rip, or cyclic universes that begin anew. At present, observations suggest that expansion will continue indefinitely. Time will stretch onward, even as structure fades. And yet, meaning does not vanish with scale. The universe gave rise to stars, to planets, to chemistry, to life. From simple laws, complexity emerged. From silence, awareness arose. You are part of that story. A momentary pattern of matter and energy capable of reflection, curiosity, and wonder. In the final chapters, we will bring this journey home, not to a location in space, but to a perspective, to what it means to exist in a universe like this one. For now, rest in the quiet understanding that you are living in the most luminous era the universe will ever know. Part 11. Perspective, Consciousness, and Our Place. After traveling across billions of years and unimaginable distances, we return to something very small. A single moment of awareness. The universe does not pause to notice itself. Stars form and die without reflection. Galaxies collide without memory. And yet, within this vast, indifferent cosmos, matter has arranged itself into beings capable of wonder. Consciousness, whatever its deeper nature may be, arose from the same physical laws that govern stars and atoms. Your thoughts are not separate from the universe. They are the universe, briefly observing itself. Every experience you have is shaped by processes that began billions of years ago, in stellar cores, in expanding space, in quantum fluctuations. The atoms in your body have passed through multiple stars, multiple planetary systems, multiple eras of cosmic history. Nothing about you is isolated. You are connected to every place the universe has been. Human perception, however, is limited. We evolved to navigate a narrow range of scale, neither the quantum nor the cosmic. Time feels linear. Space feels fixed. Objects feel solid. Yet these are approximations, useful stories told by the brain. In reality, everything is in motion. The Earth spins. The Sun orbits the galaxy. The galaxy moves through space. Even the atoms in your body vibrate constantly, never truly at rest. Stillness is an illusion, but a comforting one. The universe does not rush. It unfolds. Across cultures and history, humans have looked to the sky to find meaning. Myths, calendars, navigation, and philosophy were all shaped by the stars. Modern science did not remove wonder, it deepened it. We now know that the same physical laws apply everywhere we look. There is no privileged center, no edge where reality changes its rules. This uniformity is what allows understanding. And yet, there is still mystery. We do not know what dark matter truly is. We do not know why the constants of nature have the values they do. We do not know whether consciousness is inevitable or rare. Ignorance, here, is not failure. It is openness. The universe is not required to make sense to us. And yet, it has produced minds that try to understand it anyway. That alone is remarkable. In the final chapter, we will bring this journey to a gentle close, not with answers, but with perspective. Part 12, A Quiet Ending in an Infinite Store. Why? Everything you have heard is part of an ongoing process. The universe is not finished. It is still becoming. New stars will form tonight. Old ones will fade. Galaxies will drift farther apart. Long after this moment has passed, physics will continue its patient work. And yet, this moment matters. Because it is the only place where the universe is being noticed. Meaning does not come from permanence. It comes from presence. From the fact that, for a brief span of time, complexity has learned to be aware of itself. You do not need to feel small in a vast universe. Scale does not diminish significance. A single thought can be as real as a galaxy. A single life can be as meaningful as cosmic history. The universe is not hostile. It is simply vast. And within that vastness, fragile systems can arise, stars, ecosystems, civilizations, moments of kindness, quiet curiosity. Science does not tell us what to value, but it reminds us that existence itself is rare and improbable. The laws of physics did not guarantee this outcome. And yet, here you are, breathing, listening, thinking. The universe has no final destination. No planned conclusion. Only unfolding. What happens next depends, in part, on the choices made by conscious beings within it. The future is not written in the stars. It is written in time. As this journey ends, remember that you are not separate from what you have imagined. You are part of it. A pattern of matter and energy temporarily aware, quietly participating in the oldest story ever told. And when you look up at the night sky, you are not looking outward. You are looking into your own deep past, and into a universe that is still, slowly, becoming. Thank you for listening. We hope you enjoyed these sleepy facts. Have a wonderful and restful sleep.